Hi, my name is Ekaterina, and I'm going to present our work called Tight and Efficient Upper Bound on Spectral Norm of Convolution. In this paper, we have developed an accurate upper bound on spectral norm of convolutional layers. This new upper bound is independent of input image resolution, differentiable, and can be efficiently calculated during training. Controlling Lipschitz constant of convolutional layers is a way to make models more robust to input perturbations, increase generalization performance, and prevent explosion of the gradients during backpropagation. Lipschitz constant of a convolutional layer is equal to the spectral norm of T Jacobian, which we denote by T. However, controlling spectral norm of T is computationally challenging. We will consider the convolution of image of size n times n with a convolutional kernel K. Its Jacobian T is a double block Toeplitz matrix, which is shown in the picture. Computation of the spectral norm of Jacobian T typically requires order n squared operations. In other words, it can take quite much time if image size is large. Our main result will be formulated in terms of the spectral norm of a tensor. We introduce the following multilinear functional, which multiplies the d-dimensional tensor A by vectors u sub I and produces a number. Spectral norm of a matrix is defined as a supremum of this functional over two vectors of unit norm. Spectral norm naturally extends from matrices to the tensors. For a d-dimensional tensor, it is defined as a supremum over d unit norm vectors. We note that suprema over complex and real vectors do not coincide for some tensors. We present such example in our paper. Spectral norm of a tensor can be computed with the higher-order power method, which is an extension of the classical power method. The algorithm starts with randomly initialized singular vectors and updates one of the vectors in each iteration. In our case, singular vectors of a tensor are complex, so we have the complex conjugate operation. Our main contribution is the following theorem. The spectral norm of a convolution with Jacobian T is lower bounded and upper bounded by the spectral norm of the kernel K multiplied by constant factors. The picture illustrates this inequality for a kernel with two input and one output channel and spatial dimensions equal to 3. Our main result naturally extends for convolutions with stride. One needs to part initial kernel K with zeros and reshape it to get new kernel Q. In addition, the bound straightforwardly generalizes to convolutions with more than two spatial dimensions. Now I'm going to discuss how our tensor norm bound is connected to tensor unfoldings. The authors of Fantastic Four propose to bound the spectral norm of circular convolution with a minimum of spectral norms of 4 kernel unfoldings. However, spectral norm of any unfolding of a tensor upper bounds its spectral norm. Therefore, our tensor norm bound is theoretically guaranteed to be more accurate than Fantastic Four bound. The following table shows the values of the bounds for the kernels of different sizes. In the right columns, we can see the ratio of the bounds to the exact value of spectral norm. We observe that in practice, tensor norm is much more accurate than Fantastic Four. In addition to accuracy, our tensor norm bound is independent of input size n, differentiable, fast to compute, and applicable for convolution with any padding. We studied the effect of regularization with our new bound on image classification accuracy. We applied the sum of estimates of the spectral norms of all convolution layers of the network as a regularizer. The tables below show that regularization increases accuracy of ResNets trained on CFAR 100 and ImageNet. Throughout training, the tensor norm bound appears to be more precise than Fantastic Four. Regularization with our bound significantly decreases the singular value of convolutions and reduces the norm of composition of convolution with the subsequent batch normalization layer. The tensor norm can be used for constructing laws that imposes convolution orthogonality. In the previous works, orthogonality of convolutional layers has been shown to improve training stability of CNNs and reduce feature redundancy. We show that our orthogonal loss increases accuracy of ResNet. That's all. Thank you for your attention. Come to see our poster.